All right, here's our first homework video for Unit 3. Talking about finding critical points. Finding critical points of f, just any function. And what are you finding? We are finding possible max-min locations. And how do we find them is these possible max-min locations have a commonality. Their derivative is either 0 or it's undefined. So all we're going to do is take derivatives and set them equal to 0. Now let's start with 2x minus 3. This is interesting because its derivative is just 2. If I set this equal to 0, there's no solutions. That means there's no critical points. This should make sense because 2x minus 3 is just a straight line. There are no maxes and mins on a straight line. It's just ever increasing at a slope. So this is not a concern of ours. All right, next one. This is a parabola. So I know there is a min or a max in a parabola. When I take the derivative, I'll set it equal to 0. Don't forget to see when it's undefined, but undefined is a situation where your denominator equals 0. Since I do not have a denominator, I can just ignore this. So add 3, divide by 2, 3 halves. Let's look at this guy. I think I ended up doing this incorrectly. But let's see. Might be a good example of how sometimes we're not able to factor. Five and 1 don't add up to get minus 2. Reminding you, let's say I had my calculator. You will be asked to solve equations like this that are unsolvable by hand on a calculator portion of the AP exam. Now, you don't have to worry about that for your test because we're not going to have a calculator for our test. We'll start working with calculators as we get closer to the midterm and in the second semester. But just as a reminder, if I wanted to solve this equation, you can take the left side, graph y equals the left side. You graph y equals the right side. We see when the left side equals the right side. So when does the left side produce a y value that is equal to this y value of 0? All we need to do is find the intersections. So I got 3 times x squared minus 2x minus 5, 0. Second calc intersect. Let's go over to this one over here. There's 1. Go to this one over here. There's the other one. We will discuss in the future how you can solve any equation using your calculator, its graphing capabilities, and its ability to find intersections. So that is how we're going to solve tough equations. But for now, don't worry about it too much for your quiz or anything else. Think about this. All right, let's see this guy. Hopefully this one works out. 3 times 1/3 is just 1, so this is x squared. 2 times 5 is just 5. 6. This is nice. There's no denominator. Don't have to worry about that. I can factor this easily. So this has possible maxes and mins at -3 and at -2. Let's see, this guy, 6x squared plus 6x minus 12. I would factor out the 6. No denominator, don't have to worry about that. Factor this, x plus 2x minus 1. The 6 does not mean x equals 0 as a solution. I just have -2 and 1. Okay, 0 would not solve this equation. Let's see, this one. 4 times 4/5 times 5 is 4. 4/3 times 3 is 4. Factor out a 4x squared. I'll get x squared minus 1. Set that equal to 0. Or see when it's undefined. Don't have to worry about that. I will be able to factor this to be x plus 1, x minus 1. I will see that 0 can be plugged in. So as opposed to this one, where I just factor out a 6, it does not mean 0 is a factor, 0 is a solution. When I factor out an x, that means 0 is a solution. Because if I plug in 0 here, I will get 0 times something times something. So I have 0, -1, and 1. All right, sine x plus cos x. It's important to keep track of your signs of these derivatives. Tangent slope generator for sine is cosine. Tangent slope generator for cosine is negative sine. Don't have to worry about the undefined part. This ends up being when in cosine or sine are opposites of each other. No, it's not. It's like when sine and cosine going to produce the same value. One way to get the answers is like, okay, this needs to be positive. This needs to be like also positive because you take the opposite of the sign. You can think about that to get your answers pi/4 and 5 pi/4. But another way to do it is maybe move the sign over by adding, maybe divide by cosine. One is tangent 1, tangent's 1 in the first and the third quadrants. So maybe you do that. Let's look at this guy. Got a quotient. Got to use a quotient rule. Can't forget our rules. We spent all last unit learning our rules, so we can't forget them. Derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared. We're going to see when that's 0 or undefined. Now, since I have a fraction, the undefined part does come into play, where the denominator could equal 0. Now, x squared plus 1 is never equal to 0. There are no values where this is equal to 0. And just like how there's no values where this is equal to 0, so there's like no vertical asymptote, so there's no undefined tangents. So we actually don't have to worry about that because it's never 0. So I just have to worry about the numerator. I get -4x squared plus 4 equals 0. Subtract 4 divided by 1. I get x squared is equal to 1. So x could equal -1 or +1. All right. Oh, that's a good one. Chain. Let's use the chain rule. Outsides, insides. Don't forget your rules. derivative of the outside, leave the inside alone, times the derivative of the inside, set this equal to 0, or C when it's undefined. Fortunately, we don't have to worry about the undefined. There's no denominator. But I have 6x, x squared minus 1 squared. That's 6x times x plus 1 times x minus 1. That's all being squared. It doesn't really matter that it's squared, as long as we understand that 0, -1, and 1 would just be like solutions with a certain multiplicity, which is not that important right now. So, as long as we get these three answers, we're good. This guy, x to the 1/2, its derivative 1/2 x to the -1/2. Now, make sure we remember this piece, because this has a denominator. It's got the 1/2 root x. When x is 0, 2 root x equals 0, and f prime is undefined. So x is 0 is one of our critical points. Now, to find the other ones, I need to solve this equation. You could flip both sides. Sorry, this is an x. I like to flip both sides. Divide by 2. Square both sides. There's the other one. Let's see this guy. 2/3 x to the -1/3 plus 2. That will equal 0 or undefined. Don't forget about this, because when x is 0, sorry, make sure over here we list off 0 as another one. When x is 0, we'll have a 0 in the denominator. Our derivative will be undefined. Okay, so that's one. Now the other one is when this equals 0. I'll solve this equation, subtract the 2, flip both sides if you want to. Multiply by 2, divide by 3, how do you get rid of the 1/3 power? We cube it, because a 1/3 times 3 is 1. When I cube a negative, it retains its sign. This becomes -1/27. So that and 0 are our critical points. So this guy, so we 1/3 x to the -2/3 minus 1/27. This equals 0 or is undefined. Let's not forget about this, because when x is 0 again, 3x to the 2/3 equals 0. So this is a critical point. We'll solve the other equation, equal to 0. Add 1/27. We can flip both sides. Divide by 3. Now, how do I deal with this x to the 2/3? Take both sides to the 3/2, because 2/3 times 3/2 is just 1, and this is what we have to do. Now we got to be careful. We will get 9 to the 3/2, so this is like the 9 to the 1/2 cubed, which we can do. You could also do 9 cubed square rooted, but probably more difficult to do that. I know that 9 to the 1/2 is 3. 3 cubed is 27. I get 27. But be careful. can I have 27 and negative 27? Let's think about it. Negative 27 to the 2/3. Is that going to give me positive 9? Let's see. That's going to be the same as negative 27 cube rooted squared. Well, I can take the cube root of a negative number. That's going to be negative 3. And I can take negative 3 and square it. That's going to be positive 9. So yes, I need a plus or minus here, which means I get 27, negative 27, and 0 as critical points. What are the conditions that guarantee the mean value theorem can be applied to a function on an interval? Function must be differentiable.
I come in for junior hour today.
If the function is differentiable, then the mean value theorem applies. Recall the mean value theorem means start with 2 points, similar to the intermediate value theorem. Connect them in a smooth way. You are guaranteed to have a secant slope and a tangent slope that equal each other or parallel to each other, at least one. If f of x is twice differentiable, you're going to see this often on tests, things saying things are twice differentiable. This sometimes confuses students, but don't let it confuse you. It just means that you could take the derivative twice at any point, which means f is differentiable and f prime is differentiable. It just means you can take the derivative. So it's very much so continuous. Or not really continuous. I mean, it is continuous, but I'll say it's very much so differentiable. Not designed to be confusing. It's not the second derivative. This is it just means it can be the derivative can be taken twice. I say it should not be confusing, or it should not confuse you. We got f of 3 is equal to 8, f of 5 is equal to negative 5. State what is guaranteed to occur on the function by the mean value theorem. All right, well, instantaneous rate of change has to equal the average rate of change. Let's be a little bit more specific about the average rate of change we expect to see. I have negative 5 minus 8. I'm going from 8 down to negative 5, so that's a change of negative 13. And then I got a change of 5 minus 3, which is 2. So I'm going to have some derivative that will equal negative 13 halves, where x is between 3 and 5. That's it. Find the value guaranteed by the mean value theorem on the interval. Okay, so we just need to equate tangent slopes to secant slopes. All we need to do is a little bit of legwork for the secant slope, and then solve an equation. So let's do the legwork. I got 2 points, f of 3, which is 9 minus 9 plus 2, that's 2. F of negative 2 is 4, plus 6 is 10, plus 2 is 12. The secant slope, 12, I guess it should be 2 minus 12. I've gone down 10. 3 minus negative 2 over 5, that's negative 2. I'm going to see when my tangent slope generator generates that tangent slope. Add 3, divide by 2. I get that. That looks right. 4, 6, 12, 2, 12, 3 to negative 2. Yep. Okay. Notice this value, which is guaranteed, is inside your interval. We're not surprised. It's guaranteed that it's going to be inside the interval. So mean value theorem works. Okay. I messed up. Didn't really mess up, but before I even start with this mean value theorem, I need to confirm f of x is differentiable. Well, how we can make sure it's differentiable is by looking at the derivative and making sure the derivative is continuous. Since the derivative is continuous, there exists a derivative for this everywhere. So since there is a derivative everywhere, since I can plug in any x into f prime, there is a tangent slope for every single value of f of x. So since a derivative is continuous, the function is differentiable. It's important to kind of make sure we check. When you're told that a function is twice differentiable, that means yes, it's differentiable, that's great. You don't have to confirm. But here, I should confirm that the function is differentiable. I'll do that in a second. I mean, it's pretty easy. You look at your tangent slope generator, 3x squared minus 5. And this is continuous. And since the derivative is continuous, the original function is differentiable. All right, so since that's differentiable, we can apply the mean value theorem. Let's find our 2 points. 27 minus 15 is 12, and f of 1 would be 1 minus 5, which is negative 4. So I'm going up. Here's my slope of my secant, my average rate of change. 12 minus negative 4, I'm going up 16 over the course of 2 x units. So up 16 over 2, I have an average rate of change of 8 y's per x. Here's my instantaneous rate of change. When is my instantaneous rate of change going to be equal to my average rate of change? Add 5, 13, divide by 3, 13 thirds, square root, plus or minus root 13 thirds. I would only list the positive root 13 over 3, which is in the interval. From 1 to 3. Okay. Next. So 2/3 from 0 to 1. Let's see. Now this is interesting. I got 2/3 x to the negative 1/3, which is 2 over 3 x to the 1/3. X is 0. This doesn't have a tangent slope. So we are not differentiable everywhere in this interval. We are not differentiable at x equals 0. We'll find that we have a vertical tangent at x equals 0, because like 2 over 0 is is approaching infinity, so vertical tangent. It should not matter though, because we're talking about inside this interval. So we should be able to still find a value. So let's see, what is our secant slope? I have f of 1, which is 1. I have f of 0, which is 0. So I have the slope of the secant, which is 1. So I should be able to solve this and get a value that is between 0 and 1. cube both sides, I get 8/27. 8/27 is in the interval. Let's see, root x. Not differentiable at 0, but differentiable definitely between 4 and 16. 1/2 x to the negative 1/2, 1/2 root x. We are definitely differentiable in the interval. Why? Because we're continuous in the interval. We have our 2 points. Remember, the square root of 16 is just 4. It's only when we're solving x squared equals 16 that we'll have plus and minus 4. Square root of 4 is just 2. So I have gone up 2 y's over the course of 12 x's. Or up 1/6 of a y per x. On average, when does my instantaneous rate of change equal that average rate of change? Flip both sides, divide by 2, square both sides. 9. There you go, in the interval. Given the graph, draw your understanding of the mean value theorem for the given interval. From 0 to 3. All right, so here's a function. Here's a point at 0. Here's a point at 3. Here is my secant slope. We are going to approximate the location where my tangent slope equals that secant slope. I would say at around x equals 1. We have a tangent slope parallel to / equal to that secant slope. We got 1. 1, 2, 3. Whoa, this is like a Rolle's theorem. It looks like my y's are the same. We are looking at when a tangent is horizontal. I'm thinking at x equals 2. We got -1 to 2. So from -1, here's my point there, to 2, there's my point there. My average rate of change would be represented by the slope of this secant line, my instantaneous rate of change, somewhere around here. Maybe at 1. Doesn't matter as long as we kind of understand what's going on. From -1 to 2 here. Here's my secant line. Average rate of change is the slope of that line. Somewhere around here, maybe like 0.5. Super important to know. As long as you can draw the picture, I'm good. The following function does not have a point where the tangent slope equals the secant slope. Why does this not defy the mean value theorem? Well, let's look at this function. Okay, so this would be the secant slope. We probably need an interval from like -1 to 3. So if I talked about -1 to 3, I think I had the 2 points, but I forgot to list off the interval. I do not have a tangent slope that equals the secant slope. Why does this not defy? Well, I look at this point right here. This is a sharp point, which means f of x is not differentiable everywhere in the interval. Therefore, the mean value theorem might work, but it might not. The mean value theorem cannot be applied. Okay. And that's it. Thank you.